Hi everyone, I am Rohit Kumar Singh, the teaching assistant for the course Experimental Physics 2. This is the fourth live session, and last in the last session I mainly talked about optics. I mean some basic concepts of lens and I tried to solve some problems based on some concepts of lens like thin lens formula and lens maker formula, etc. So today also I'll discuss more problems on optics and I'll also recap some of the concepts. Okay, so let's start. Mhm. So, so the optics that I'm going to discuss today is mainly in ray optics, and in ray optics we mainly study uh, how the uh, ray of light bends and converge, diverge when we place some objects like lenses, mirrors in the path of the ray. Okay, so and there are many uh, you know applications of ray optics in everyday life. So, uh, so, the first, so for the mirrors, so we have basically two types of mirrors. I mean, uh, besides the plain mirror that we all have in our home. So there are two special types of mirrors. Uh, First is called concave mirror. So, so concave mirror is silvered on the outer side, and if parallel ray of light are coming like this, they they converges to a point. Okay, like this. So this is the concave mirror. Okay, and then there is another type of mirror which is curved mirror, which is called convex, and here this inner part of the mirror is silver, and so parallel light which are coming from infinity like this, they get diverged. Okay, so, and you can backtrace them to see where they find their focus. And and there is a formula called mirror formula, which relates the object distance, image distance, and the focal length of the mirror. Okay, so this is the mirror formula. It's the same like the lens formula, but just the sign, just this plus sign. Okay, and then we have the formula for magnification, which is, so magnification is height of the image by height of the object, I mean, is the ratio of height of the image and height of the object, and it's also equal to the image distance and the object distance. But there is a negative sign, and so for mirror, this is always true. Okay? And also there is one more thing. So the focus is always okay, this is the convex mirror. Focal length is always half of the radius of the curvature of the mirrors. Okay, so this one should remember, small detail. Now, the concave mirror. So suppose this is the principal axis. Here our pole, and suppose light rays are coming like this from infinity parallel to the principal axis, and they get converged to a point, and this point is called focus. Okay, and from pole to focus is the focal length. Okay, so the concave mirror, in case of the concave mirror, the image is always real and inverted. Okay, uh, because image is always formed, uh, on the same side as the object. So it is always real and it will be inverted. But in the case of convex mirror, so convex mirror has this side silver. This is the principal axis, pole, and light rays coming from infinity like this. So what happen is they diverge, okay, and the image which is formed. So to find the image formed, oh, sorry, yeah, we have to back trace this like this, okay, and then here we find the focus of this mirror. So you see this focus is on the other side of the mirror, and so it's the image that is formed by convex mirror is always virtual and it's erect. Okay, so this you might be knowing already, but just to remind you. Okay, anyone has any question here? Parshuraman, do you have any question? These are very basic things. Okay, thank you. So let's go to, now I want to discuss a little bit of another concept called refraction. So, so what is refraction? So refraction is a phenomenon uh, when light light ray uh, traverse two mediums which have different refractive index. Uh, Refractive index is a measure of optical density. Okay, so what does it mean is, so suppose this is a medium A, and the medium B is below. Okay, and this is the normal on the interface, and suppose the light ray is coming like this. Okay, and this is the angle of incidence. So if B is optically denser than A, then this light ray will bend towards the normal. Okay, like this. So it should have gone like this, but because B is optically denser than A, it bends like this, and this is the reflection angle of reflection. Okay, and there is a formula which relates all of these. So which relates the angle of incidence, angle of refraction, and the refractive index of A and B, and it is given as sine I upon sine R is equal to refractive index of A with respect to B. Okay, and this is called Snell's law. Okay, now this Snell's law is applicable to uh, all the all the materials. Okay, sometimes what can happen is A can be optically denser than B. In that case, this light ray can move away from the normal like this. Okay, so it is valid for everything. Now, uh, no, no. So we can use this uh, concept of refraction to manipulate the light rays. Okay, so how can we do that? Uh, so we use lenses. Okay, so this is a convex lens. Okay, let me make it little bigger. So symmetrical. Yeah, okay, it's perfect. So uh, convex lens. Now, what convex lens does is, so suppose there is a light ray coming from infinity, parallel light. Okay, so and suppose this is air, the medium A, and lens is made up of glass, so it is optically denser than air. And here on the lens, this is the normal, right? This is the normal direction. So what will happen is this light ray will bend towards normal like this, right? And then it will go here, and now again here normal is like this, right? And now now it is going from the lens to air, so it will bend away from the normal, right? So it will bend again to this side, right? And so what, see what is happening, the ray that was going like this has now followed sorry has now followed this path, right? So what is this lens is doing is it is focusing the light rays. Okay, so suppose another light ray coming like this, it will also bend like this. Here light ray coming like this, it will bend like this, right? So so this is what happened in case of the uh, convex lens. It converges the light rays. Okay, and so let me draw a simple diagram of convergence. So and the point where the light rays get converged is the focus of this lens. Okay, and similarly you have concave lens. So in case of concave lens, so suppose now light ray is coming like this. Okay, and now here the normal is like this, right? So light ray instead of going like this, it will bend towards the normal like this, and then again uh, from here lens to air, and normal is this, so it will bend towards the normal. So you see what is happening is the light ray instead of going like this, it's going like this, right? So it is diverging. So similarly here it will diverge like this, and you can trace it back here, and you can find the focus of this. Okay, so um, this is the concave lens, and it is also called the diverging lens. Okay, so yeah, you can see convex lens converges the light, and concave lens diverges the light rays. Okay, and there is a formula which relates the focus, the radius of curvature. So you see there are two radius of curvature because there are two curved parts here, this side and this side. So the radius of curvature and the refractive index of the lenses. So the formula is like this. So 1 upon f is n minus 1. N is the refractive index of the lens, 1 minus r1. So r1 and r2 are the radius of curvature, and this formula is called lens maker's formula. Okay, so and one can derive from this formula another formula which is called the thin lens formula. So it is given like this. This is the thin lens formula. Okay, it relates the image distance v, object distance u, and the focal length f. Okay. So this I also discussed in the last live session, and one more thing I discussed, it was for convex lens, uh, when image is real and inverted, magnification is given by this formula. Okay, so this negative sign will be there when the image is real, because the image is all formed on the same side as that of object, so negative sign will be there. And for concave lens also, and when image is virtual, so for convex lens image can be both real and virtual. So when the image is virtual, magnification will be I by O equal to V by U. And for convex lens, since the image is always virtual, only this case applies. Okay, so just to keep in mind. Okay, so yeah, I mean these are the few concepts that you need for today's problem solving session. Okay, so let's uh, let's go to our first problem. Here the first problem is a convex lens of focal length 20 centimeter forms a real inverted image of a needle at a distance 50 centimeter from it. Where should the object be placed in front of the lens to produce a real image of the same size as that of object in same place as that of object? Okay, so this I discussed last time also. So suppose this is a convex lens and its focal length is given. uh, Focal length is 20 centimeter. Okay, and a real inverted image of needle at a distance 50 centimeter from it. Okay, uh, so here two information is given. So focal length is 20 centimeter and there is a image image distance that is given. So V is given 50 centimeter. Okay, so but I mean we don't need this information really, because so the question is where should the object be placed in front of lens to produce a real image of the same size as that of the object and in the same place as that of object. So there is a property of convex lenses that if you place an object at, so suppose 2f distance from the center of the lens, this will produce an image and real image at the same of the same size and in the same place as that of the object. Okay, so suppose this is our uh, object, so one light will go like this. Okay, and wait, this is a convex lens. Okay. Mm. Yeah, this will go like this, and then suppose, and here also we have this distance 2f. Okay, so one this will one light will go like this, and another uh, another light might so like go like this, and this will pass through here, and you will get an image here which will be inverted and real. So basically for convex lens, when u is equal to 2f, the object and image are of same size and in same place. Okay, so the answer will be simply 40 centimeter. Okay, this was an easy question. Now the second question. So here a concave lens, a concave mirror produces 3 times magnified real image of object placed at 10 centimeter in front of it. Okay, where is the image located? So there is a concave mirror. This is a concave mirror, and there is an object located at 10 centimeter front of it. This is the object. Okay, this is 10 centimeter, and the magnification is, so it produces a 3 times magnified real image of the object. Okay, so magnification is given 3, which is, as I have told you, so magnification formula is simply h prime by h. Okay, which is equal to minus v by u, and so and this is 3. Okay, now we have already given here u, which is the image distance, as minus 10 centimeters. Remember, we are measuring distance opposite to the incident light, so it will be negative. And so we can calculate the image distance simply from this formula, which is minus v is equal to 3 into minus 10. So b and oh sorry, uh, this yeah, and this minus, so this 3 will be negative because see, this h prime is because this image is inverted, right? uh, is real. It's real and inverted, so this h prime will come with a negative sign. So there are three negative signs, 2 will cancel and we'll have minus 30 centimeter. So this is the image distance, and this negative signs denote that it's an inverted image, and yeah, it forms at 30 centimeter in front of the, somewhere here it will get formed. Okay, it will be inverted 3 times size of this object, and 30 centimeter. So yeah, this one is also an easy problem. Now we have a match the column problem. So the question is, match the items given in column 1 with one or more items of column 2. Okay, so first in column 1 we have P. In P we have a plane mirror. Then here the options are: used as a magnifying glass, no; can form images of objects spread over a large area, no; used by dentists to see enlarged image of teeth, no; plane mirror cannot enlarge on an object. Then the image is always inverted and magnified. This is also not true. Plane mirror cannot magnify the images. Then the fifth option is the image is erect and of the same size as the object. Yeah, this seems true. The plane mirror, in plane mirror you always see the image whenever you look at the mirror in your home. The image is erect and it is of the same size as us. Okay, so yeah, the P goes to B. Okay, I mean fifth. Then for Q, a convex mirror. So as you know, convex mirror sorry, a convex mirror forms always a virtual image. Okay, so and virtual images are sorry, and virtual image, and they are diminished in size, right? So since they are diminished, they can cover a large area. So Q will match to 2. Okay, can form image of objects spread over a large area. So you have a convex mirror. Suppose in so at a crossing on the road, you might have seen a convex mirror. It is to help the uh, so suppose there is a T point at in the road, and so the incoming vehicles can see which vehicle are coming from which side. So yeah, these mirrors are helpful there. Then a convex lens. So convex lens, convex lens. Wait, someone joined. Hello, Sandeep. Can you hear me? Yeah, okay. So why you are so late?
Sir, I have some signal issues.
Okay, okay, okay. Now it's good.
Yes, sir, I can.
Okay, okay. So I was discussing this third problem. Okay. So let me go over it once again. So it's a matching the column problem. Okay. And here the first option on column 1 is a plane mirror, and then it matches to column 2 at fifth option, which says the image is erect and of the same size of the object. It is trivial. Plane mirror always forms an erect image, and the size of the object as the size of the object. Then a convex mirror forms a diminished image, so it can cover a large area. So Q matches to 2. Then a convex lens is a converging lens, and it can form a magnified image of the object, right? If the object is placed at uh, suppose near so this is the focal length. If the object is here, it can magnify it if you are looking from here. So how do you make a eye? So sorry. Yeah, so if you're looking from here, this object will seem magnified. So this is used as a magnifying glass. Okay, so R matches to 1. And then a concave mirror. So a concave mirror is also used to form enlarged image. So if you have ever been to dentist, you might have seen them using this concave mirror on their forehead. So to enlarge the image of teeth, so that they can look carefully at the cavities and everything. So yeah, if the so for a concave mirror, so this is suppose a concave mirror, and your object is placed between pole and focus, and so this will diverge the rays. So this is the diverge the rays, and you will get an enlarged image, right? Okay. So yeah, concave mirror used by dentist to see enlarged image of teeth. So yeah, this is a simple problem. Do you have any doubt here?
Sir,
Hmm.
please explain plane mirror and convex mirror.
Please explain.
Plane mirror and convex mirror.
Plane mirror is simple mirror that you have in your home. Okay,
Okay, sir.
and convex mirror is so this is concave mirror. Okay, so if you have a spherical mirror and you silver this side of the mirror, you get a concave mirror. Concave mirror, the property of concave mirror are this. So suppose these are parallel rays coming from infinity. Okay, it will converge them all to a single point called the focus. Okay, so it is a converging mirror, and it always form real and inverted image. Okay, and if you have, so suppose the same mirror, if you silver this side, okay, so you get a convex mirror. This is concave mirror. Okay, and suppose the light rays coming from infinity, parallel rays, they will diverge. Okay, so and so you have to extrapolate it behind, and you will get a real and sorry, virtual and erect image of the object. Okay, so this is a diverging lens, diverging mirror. You have you studied ray optics in class 12th? Maybe.
Yes, sir. Yes, sir.
So you might remember these things, right?
Okay, sir. Okay, sir.
Yeah. Yeah. If you have any more doubt, you can ask. Okay.
Okay, sir.
Okay. So let's go to the next question. Okay. So here the question is, a small candle 5 centimeter in size is placed at 18 centimeter in front of a concave mirror. Okay, so you have a concave mirror like this, and at 18 centimeters, so this is the object distance, and this is a candle. Okay, suppose this is a candle, 5 centimeter of height. It is placed in front of a concave mirror, and the curvature, radius of curvature is given as 30 centimeter. Do you know what radius of curvature is, Sandeep?
Yeah, sir.
What what is the radius of curvature? What do you define as radius of
It
curvature?
is it is the divided by 2, sir.
It is the
Half of the part of focal length.
yeah. I mean, okay. I couldn't hear you. So if you complete this into a circle, okay, this is a spherical mirror. So it will have some radius, right? It will form a,
Actually, the relation between R is equals to 2F, sir.
yeah, between focus and radius, I know, but I was asking what radius of curvature means. So this is a spherical lens. If you complete it, so it is made up of a spherical glass, right? So the radius of that sphere is called the radius of curvature. Okay.
Okay, sir.
Yeah. Okay. So the question is, at what distance from the mirror should a screen be placed in order to obtain a sharp image? Okay. So it's asking that where should we place the uh, object? Okay, at what a mirror should be, wait, screen, yeah. So where should we place the screen to object? So it's basically asking the image distance, right? Because the concave mirror form a real image, we can obtain it on a screen. So where would we put our screen to get a image there? Okay, so basically here object distance is given minus 18 centimeter. We are asked V, the image distance. Okay, And since r is given, you can calculate the focal length by dividing it by 2. So 15 centimeter is the focal length, right? And it will be in negative because it is. So do you know why we are taking negative sign here? Sandeep?
From the relation 1 by f is equals to 1 by u plus 1 by v square.
No, but why we are taking this focal length as negative? This minus sign, why we are putting? Do you know why, how the sign convention work? So here basically the distance measured towards the incident ray are positive, okay, and opposite to the incident light is negative. So since we are measuring the distance from the pole of the mirror, on the left side all the distances will be negative, okay, this you remember, keep in mind. So now we have this mirror formula, and V is unknown, and we know U minus 18 centimeter and F is minus 15 centimeter. Okay, you can solve this. 1 by V is equal to, so this will be 90, 5 minus 6. V is simply minus 90 centimeter. Okay, so that means the image will be formed at 90 centimeters somewhere here, and it will be real and inverted, and it will be here. So this will be your 90 centimeter. Okay, any doubt here? Simple problem. Just you have to remember the sign convention properly. Is it fine?
Yes, sir. Yes, sir.
Okay, thank you. Now, fifth problem. So the fifth problem we have is a 10 centimeter needle is placed vertically 10 centimeter away from a convex mirror of focal length 15 centimeter. So here we have a convex lens, convex mirror, sorry. So convex mirror is silvered like this, okay. At 10 centimeter from here, from the pole, we have a needle which is 10 centimeter in height, okay, and its focal length is 15 centimeter, okay. So we have object distance as 10 centimeter and focal length as 15 centimeter. Right. Okay, now we have to find the position and size of the image. So again we have the mirror formula, 1 by V plus 1 by U equal to 1 by F, and we know U and F, so we can calculate V. So V will be simply 1 by, so this focal length is 1 by 15, and minus 1 by 10, okay. Yeah, we can calculate it. So this will be 30 2 minus 3 minus 1 by 3 1 by v. Did I do something wrong? Answer is not matching. Away from a convex mirror of focal length 15 centimeter. Oh, sorry. Okay, this focal length will be negative. Okay, tell me why. Because focal length is always,
Because of sine convention rules.
yeah, focal length is always measured this side, right? This is the focal
Yes,
length.
sir.
So that's why this will be negative. And so this will be minus 5 by 30. So this will be minus 6 centimeter. Okay. So
Okay, sir.
the correct option will be 6 centimeter. Yeah. And because it is negative, the image will be formed this side of the mirror, right? So
Yes, sir.
opposite side of the mirror. And okay, and we also have to know the size. So size is given by, so size of the object by size of the uh, uh, size of the image by size of the object is equal to minus v by u. You know this formula, magnification formula?
Yes, sir. Yes.
Yeah. And
Magnification.
yeah, and we have this size of the object, which is h2 10, h1 we want to know, and we have calculated minus v 6, and u is 10 again, 10 cancel, and so size of the image is just 6 centimeter, right? So yeah, this C option is correct. Okay.
Okay, sir.
Okay. Okay, this is also a simple problem. Then sixth problem we have. So the problem says a tank is filled with a liquid to a height of 18 centimeters. So suppose this is a tank, and this is 18 centimeter. Okay. The apparent depth of a needle lying at the bottom. So suppose there is a needle lying at the bottom of the tank is measured by a microscope to be 12 centimeter. Okay. So have you ever noticed if you have a bucket full of water and you put something in it, like you put a suppose a spoon inside it, you will see that the depth of the depth that you can see is less than what the actual depth is, right? The bottom seems to be somewhat above what the actual bottom is, right? The depth diminishes. Have you ever noticed in a bucket full of water?
Yes, sir.
Yeah. So why does that happen? So it's happened because of this property of refraction, right? Because
Yes, sir.
the light ray, so suppose this is the normal, so the light ray which are going so from the object, it will refract, right? It will refract,
Towards the normal, sir.
yeah, away from the normal, right?
Okay, sir.
And the image will be formed here. See,
Yes.
the image will be formed here.
Okay, sir.
So because of this, we get this sense of false depth, okay, which is called apparent depth. And and it depends on the refractive index, okay. So
Okay.
the refractive index is simply the ratio of the real depth and the
I have little bit confusion.
okay, tell me.
Okay, sir. After completion of this question, I have some little bit doubts, sir,
Yeah, yeah,
about
sure,
this
sure.
rare Armenian and denser medium.
Sure, sure, sure. So yeah,
Like will
this
be
is yes, this is it. Like so, just you can divide these two. So the real depth is 18 centimeter. The apparent depth is 12. So you get the answer as 3 by 2, which is 1.5 C. B. Okay. Yeah. Now tell me what is your doubt.
sir, I have little bit confused that how the rare medium and the denser medium, how the light ray will be away from the normal towards the normal. Can
Okay,
you
okay,
explain,
okay,
sir?
okay, okay, okay. Yeah, yeah, sure. So, you know the Snell's law. So, what Snell's law says is, so suppose
Yeah.
this is air, okay, and this is a denser medium, say water, okay, and this is called interface. This line separating them, okay. So, suppose a light ray is coming like this, okay,
Okay, sir.
and so what will happen now is that because this is a denser medium, uh, the speed of light will be slower here, okay, and due to that it bends towards the normal, okay. Suppose if it would have gone straight, this path would have been followed, but now it will follow this path, okay.
Okay, sir.
And this angle called incident angle, and this is called the refracted angle, and there is a relation between them. So sine I by sine r, it is given by mu
And to
air, I mean the relative uh, refractive
refractive
index,
index.
mu air by mu water, okay. So
Okay, sir.
if you know mu air is just 1, so it will be just the refractive index of water, okay. So this is the Snell's law, and same thing will happen in the reverse case. So suppose the light is going from this side now, okay, from the water. So instead of going this way, it will move away from the normal, okay, in the air, okay. So because it is going from a denser to rarer medium. Understood?
Yes, sir. Yes, sir.
Yeah. So yeah, this is a simple refraction concept.
Okay.
Now then we have the seventh problem. It says a small bulb is placed at the bottom of a tank containing water to a depth of 7 centimeter. What is the area of the surface of water through which light from the bulb can emerge out? Refractive index of water is given 4 by 3, okay, and consider the bulb to a point source. So point source is something from which light comes from all direction like this, okay. So do you understand the question?
Yes, sir.
Okay, what does it ask? Can you explain a little bit?
Suppose if you take a tank full of water,
Okay.
not full of water, some containing some water,
Yeah.
and a small bulb is placed in that vessel, not vessel, in that containing tank,
Mm-hmm.
and the surface area through the
Mm-hmm.
light, the light of the bulb can be transferred
Okay, yeah.
through the
Yeah,
surface
yeah,
of the
yeah, yeah.
water.
Yeah. Emerge from the. So, I mean, this,
Yes,
the light source will come like this from this bulb, right?
yes, sir, yes, sir.
In all direction it will come like this, like this, like this. But all the light that is coming from this will not be visible to us, okay?
Yes, sir.
Because some lights will get internally reflected from the
Yes, sir.
surface.
Yes. Yes, sir.
So the,
There will be some.
yeah, so the surface area through which we can see the light, that we have to calculate. So
Yes, sir.
before they get totally internally reflected, there will be some critical angle at which they will just cross this, just glance the surface. Okay.
Yes, sir.
So total internal reflection, right? So total
Yes, sir.
internal reflection, so suppose this light is coming here, it will, at some critical angle it will go like this on the surface itself, on the interface itself, okay? And
Yes, sir.
if you increase now the angle more, then they will be totally internally reflected, okay?
Yes.
So we have to find this angle at which they are, uh, uh, which is critical angle, okay? And after this, whatever light will go, they will be visible outside. So that will be our surface area, right? So let me draw a better diagram. So suppose this is our tank of water. This is our point source O, okay, and this is the surface. This is the normal, okay. Let's call this point A, which is perpendicular, and suppose this is the light, okay, which is going like this, critical angle, okay. And after this, whatever light will go after that, I mean, whose angle is greater than this, they will all be visible outside, okay. And but before this, all will be totally internally reflected, correct? So let me remove all these extra. We'll keep this one because we want to see this IC, okay, this critical incident angle. We want to calculate it. Same thing will happen on this side also, just symmetric, okay, this IC, this angle, sorry, okay. Now how do you calculate it? So we can use the Snell's law, uh, right? Because sine IC by sine R. So sine R here will be what? 90 degree, right?
Yes, sir.
Yeah. And we'll have 1 by mu, because air has refractive index 1, so we'll have the refractive index of water only, Okay, so and sine 90 is just 1, right? So IC will be what? Sine inverse of 1 by mu, right?
Yes, sir.
Okay, now, and we know mu is equal to 3 by 4, it's given. Okay, so
Yes, sir.
okay, let's leave it there. Now what we have from this figure, uh, so suppose let's call it B and this is O. So AB by AO is tan IC, right? Because this is a 90-degree, so and this is hypotenuse, so this is the perpendicular and this is the base, right? And which is the ratio of which is just tan theta. Do you know this?
Yes, sir.
Yeah. So we can calculate AB by is equal to AO tan IC. Okay, and so okay, so AO and tan IC is what? Sin IC by cos IC, right? And let me do it here. And we have just mentioned here that uh, sin IC is so sin IC is what? 1 by u, right?
Yes, sir.
Here sin IC is 1 by u, and so that means 4 by, oh sorry, what is, oh sorry, mu is 4 by 3, so this is 3 by 4, 1 by mu. Okay, and we can write cos IC as 1 minus sine square IC under root. Do you know this formula? Because
Yes, sir.
cos square IC plus
Cos
sine,
square theta is equals to 1 minus sin square theta.
yeah, because this is the formula you know. Okay, so then and we can put everything here. So AO into 3 by 4 into 1 by 1 minus 3 square 4 square 9 by 16, right? And if you calculate this, you will get the answer as 3 by root 7. Okay, so the area, so what is this distance, this AB, what is it really? This AB is the radius of the circle, okay, surface. So this will form a circle, right? On the surface you will have a circle like this through which the light will come, right? And this is the AB distance. If you see the bucket from the top, see this glass slab from the top, right? It will be a circle. So the surface area will be just pi r square, and the radius is given by this AB. Correct? Do you understand, or should I explain more?
Sir, can you explain?
Okay, wait. So, as I told you, beyond this distance, all the light will be internally reflected, right? So, only up to this much distance, the light will come out, right?
Yes, sir.
But since it is a point source, the light will come out from the all directions, right? So if you see this is the top view of uh, this tank, okay? So this tank, and inside it, this is the bulb. So light will come out from all direction, na?
Yes, sir.
So it will form a circle, right?
Yes, sir.
You have to imagine it. Can you imagine it?
Yes, sir.
And the
Um,
radius of that circle is this AB, okay, from all sides. So that's why we are putting AB square here, okay? This is the surface area through which the light will come out. And you know the AO is the depth which is given 7 centimeter here, okay? So into AO square into 3 by 7 under root 7, okay? So you can put everything here into 7 square into, oh sorry, this is also square, to 9 by 7, okay? This 7 will cancel this and it will be 198 centimeters. So this is the area through which the light will come out, okay?
okay, sir.
It's a simple problem. If you have you think about it, if you still don't get it, ask me in the next Saturday, okay?
Okay, sir.
Okay. Now our eighth problem. Here we have a double convex lens, okay? So can you mute yourself? Noise is coming. When I'll ask, just unmute, okay? So we have a double convex lens. Sorry. So double convex lens means both side is this and this is convex. The curved surface are convex, and its refractive index is given as 1.4, okay? And R1 and R2, the radius of curvature is same, okay? And so the question is, what is the radius of curvature required if the focal length we want is 40 centimeter, okay? So this is the problem in which lens maker formula will be applied, so which is given as simply this. Now we want a focal length of 40 centimeter. We know the refractive index 1.4, so that 1.4 minus 1, 0.4, and R1 and R2 are same, so we can just put it like 2 by R, okay? And we can calculate for R, which will be simply, so 0.8 into 40, which is 32 centimeter, correct? So this is a simple problem. This is the radius of curvature required if we want the focal length to be 40 centimeter, okay? Any problem here? Sandeep?
No, sir. No, sir. I understood.
Okay, it's easy. Okay, we have one more learner. So yeah, we are almost I mean at 8th problem. I still have 5 more problems, so please stick and ask any question if you want. Okay, so this is our ninth problem here. Here, a beam of light converges at a point P. Okay, so we have a beam of light like this. It converges at point P. Okay. Now a lens is placed in the path of convergent beam 16 centimeter from B. So here we have put a lens, okay, 16 centimeter from P. Now at what point does the beam converge if the lens is a concave lens of focal length 20 centimeter? Okay, so this lens is a concave lens. So concave lens is looks like this. Okay, and you know that concave lens always diverge the light rays, so they diverge the light rays. Okay, so now where they will now at which point the beam will converge, that is the question. So let me write it. Let me draw the ray diagram again. Let me clear this first. Okay. So a concave lens like this. Okay, now earlier we had a beam of light coming like this. So this is when we didn't have the lens. It was converging at some point P. Okay, now when the lens is there, what it will do is it will so it will diverge the ray little bit, and now they will meet at somewhere here Q. Okay, so we want to know this distance, this distance, and we are given the focal length of lens. So can you one of you suggest how to solve this problem? And this P is given, and this is 16 centimeter. So this is a simple problem. I mean, it looks complicated, uh, but what you can do here is that, so suppose this P as your object. Okay, now consider it as a point object, and it is emitting light like this, and this light will go here. Okay, and it will diverge like this. Okay, and this and this image, and you will, this will form a image here. Okay, at Q. So you can, I mean, convert this problem into a simple object image problem. Okay, by considering your object as P, and then it will form the image at Q. Okay, and then you have U is equal to 16 centimeter, and focal length is given minus 20 centimeter, because focal length is this distance measured in the opposite direction of incident beam. And you have the thin lens formula, 1 minus V 1 minus U equal to 1 by F. So you can put everything, and you can calculate your V, and it will come at 80 centimeter. So this distance will be 80 centimeter. So that is the effect of a diverging lens. It will diverge the light rays, so that when it was converging at P, now it will converge at Q, which is a large distance than 16 centimeter. Okay. So any doubt in this problem? This is a tricky question. Uh, you'll have to apply this trick that you will have to consider your any object at P, then you can solve this problem easily. So any doubt in the here? If not, let me go to the next problem. So the 10th problem is the sharp image of a small object fixed on the wall of a room. Okay, so suppose there is a wall. There is a wall. Okay, here you have some object like this. Okay, is to be obtained on the opposite wall by means of a convex lens. Okay, so there is this opposite wall, and you have a convex lens in between, and this distance between the wall is 4 meter. Okay, now the question is, what is the maximum possible focal length of the lens required for this purpose? Okay, so we need to calculate the focal length, maximum possible. So we have to obtain the image on this other side of the wall. Okay, now how do you do this? So to get a real image of this object, what would be the condition? Minimum, so suppose this is your focal length. Okay, and as I told, I think in the first and second problem, if you have your object at suppose 2f, its image will be formed at the opposite side at 2f, right? This is the property of a convex lens, right? So we can similarly we can imagine here like this screen should be at least greater than 4f. Okay, this opposite wall, so this should be the condition. And so for focal length you will have d by 4, which is equal to just 4 by 4, 1 meter. Okay, so the focal length should be just 1 meter, maximum possible focal length. Okay, is it fine, or do you have some question here? Sandeep, is it fine?
Yes, sir, fine, sir.
Okay, thank you. So now the next problem. Here the question is, a square shaped card having sides 2 mm is placed at a distance 8 centimeter in front of a convex lens of focal length 10 centimeter. Okay, so you have a square shaped card. Okay, and then you have a convex lens. Now what does the convex lens do? It converges the light rays, okay, coming from an object, and here image will be formed like this of this square shaped card. So its dimensions are 2 mm length and breadth. Okay, and we have to find the area of this image. So again, it's a very simple problem. Since we are given this object distance u, which is minus 8 centimeter, we can calculate the image distance by using the thin lens formula, right? And the focal length is also given 10 centimeter. And so let's calculate the image distance, which is 1 by 10 plus 1 by 8. Oh sorry, it's minus plus, so then this will be minus. Okay, so it will be minus 40 centimeter. Okay, so and then sorry, 1 by 40, then image distance will be minus 40 centimeter. And magnification is given by image height by object height is equal to E by U, and which is minus 40 by minus 8 equal to 5. So the image is getting magnified 5 times, correct? And so this 2 mm length and breadth that we have, now it will become 2 into 5 times, that is 10 mm, right? And the area will be simply 10 mm square, and so in centimeter you can write it as 1 centimeter. So 10 mm square will be just 1 centimeter square. Sorry, correct? So you have to use this thin lens formula and the magnification formula to calculate this. It is also a simple problem. Is it okay? Okay. So now let's go to our next problem. This is the second last problem. Wait, let me just a second. Yeah, so here the problem is find the radius of curvature of the convex surface of a plano-convex lens whose focal length is 20 centimeter. So we have a plano-convex lens like this, and refractive index of the material of the lens is 1.6. So whenever you have information about refractive index and focal length, you can blindly use the lens maker formula, which is given by this 1 by R1 plus 1 by R2. Okay, and since this is a plano-convex lens, the R2 is infinite, right? Because this is a plane surface, so and plane surface has no curvature, so it is just infinity, and it is the R1 you have to calculate. Okay, so everything is given here. You can just put all the information. Focal length is 20 centimeter. 1.6 minus 1 is 0.6. 1 by R1, and 1 by infinity is 0, so this is just 0. Okay, and R is just 0.6 into 20, which is 12 centimeter. Okay, So this radius of curvature, you need to make a lens of focal length 20 centimeter. Uh, yeah, so plano convex lens of 20 centimeter, 12 centimeter, option C. This is also a simple problem. Any doubt here? Okay, if not, let's move on to the next problem. So I'll ask this. So you guys will tell me what is the answer of this problem. It's a very simple question. There is nothing to solve here. Okay. So the question is, a convex lens is made of a material of refractive index n1 and is kept in a medium of refractive index n2. Okay. Parallel rays are incident on the lens. Which of the following ray diagram represent the path of the rays through the lens? So tell me which figure looks appropriate to you. So first let Sandeep try. So Sandeep, can you tell me? Just think about it. So here the condition is n1 is less than n2. Okay, I just told you the laws of refraction. If this is n1, this is n2, this is a denser medium like water, the light ray will come and get what? Deflected towards the normal or away from the normal?
Towards the normal.
Yeah, towards the normal. So now then think about it. What will happen here in this lenses? The ray are coming, they will be deflected. So the n1 here is the refractive index of lens and n2 is the refractive index of the medium from which the light rays are coming, and which is greater than the refractive index of the material of the lens. So now think about it. How will, so let me draw a diagram. Okay, so suppose this beam is coming, this is the normal. Okay, which direction it will go? Will it go like this or will it go like this? One or two?
Two, sir.
Two. Okay, why? So this is a rarer medium, this is the denser medium. Okay, opposite thing is happening here. So it will go away from the normal, right? Inside the lens.
Yes, sir.
Okay, so then which figure is correct? In figure 1, 2, 3, which one is correct, do you think? First, no, not true. So like I showed here, so this n1 is the rarer medium. Okay, so light will bend away from the normal. Okay,
Sir, I think figure 2 is the correct one.
yeah, figure 2 is correct. So see, here the light is coming, it is bending away from the normal, and then you can extrapolate it, and this is the correct path of the ray. Okay, so yeah, figure 2 is correct. So yeah, this is it. This was little counterintuitive, but you have to think about it. Okay, this was the last problem, I think. Yeah, so any doubt for today's session? So those who joined late, this recording of this session will be uploaded on the YouTube. You can watch there. And if you have any question, you can ask me.
Sir,
Yeah.
sir, that YouTube channel,
Huh?
sir, recording classes in YouTube, sir.
Yeah, recording will be available on the YouTube. The link is there, I think, on the website, NPTEL website. You can check
Okay,
there. Okay.
okay, sir.
Okay. Uh, okay, then any more question?
No, sir.
Okay. Then thank you. I'll close the session. Okay. Bye.
Okay. Thanks.